This video is on weight and gravitational potential energy, and it's going to cover some of the requirements for P2.3 in GCSE physics. We're going to talk about the equation for weight, we're going to talk about what weight is, we're going to talk about the basic properties of gravitational fields, and then begin to relate that to gravitational potential energy. I will just say gravitational potential energy is a topic that's explored in more depth and more detail in P5, which is the energy topic. Okay, so without further ado, first big idea is that every object with mass has a gravitational field. So here we've got a picture that just represents a planet. In this particular case, we're going to make this Earth, our own planet, and Earth has a mass, okay? It has a rather large mass, and so as a result of that, it has a gravitational field. Now, if I was to draw Earth's gravitational field at a distance, to just give you a visual picture of it, it would look something like this. So Earth has what is called a radial field, which means the field is symmetrical in all directions, extending out from the surface of the Earth. And so when we draw that, we draw it using a diagram called field lines. Okay, so each one of these lines represents one of the Earth's gravitational field lines, and we indicate direction on here. And we draw the direction of the Earth's gravitational field lines towards the Earth. Why do we do that? Well, the reason we indicate the direction that way is we have to imagine what would happen if I put another mass, okay, so an object with mass, somewhere in Earth's gravitational field. And the crucial thing is that because any objects with mass have a gravitational field, this mass will also have a gravitational field, and it will attract to the Earth. So one of the big ideas that you should know about gravitational fields is that they are always attractive. Okay, they are always attractive. So any objects with mass will have a gravitational field. So even as a really simple example, here you can see my pen lid and my pen. These objects both have a mass. So they both have a gravitational field that right now is attracting them. Now, obviously their mass is incredibly small. So their gravitational field is very, very small. So we don't notice this effect, but I could actually calculate it. I could work out, if I knew the mass of my pen and the mass of my pen lid, how much force of a gravitational attraction is between them right now. This extends to everything. So I am obviously holding the pen lid. I have a gravitational field and the pen lid does. So there is a field of force of attraction between us right now. It's the same one that exists between the pen lid and the Earth and me and the Earth. Obviously the Earth has a much larger mass, so the effect of that gravitational field is much stronger. So big ideas I want you to get first, okay? Key properties of gravitational fields. And there are a few that I want you to make sure that you understand first. The first big one is that gravitational fields are a property of mass. They are caused by mass. Any object with a mass has a gravitational field. This is in comparison to say any object with a charge has an electric field. So when we talk about electric fields and electricity, that's caused by charge, whereas gravitational fields are caused by mass. So that's the first thing. The second thing is that they are always attractive as far as we are concerned at GCSE and even A-level. There are certain circumstances you could use some high-level hypothetical physics where you can say that it's repulsive, but generally speaking, it's always attractive. Two masses will always attract each other. The shape of this field that I've just described here, as I say, is called a radial field. That's really just bonus information, but just is something to be aware of. That's what the shape is. So what we can imagine is what would happen if I put this mass at different points in the Earth's gravitational field. Now, the other thing I could say is, well, okay, well, this mass is going to attract more strongly the closer they are. So gravitational forces are very long-ranged. They travel over very big distances, as opposed to, say, magnetic forces, which typically are much more short-range. Gravitational fields are very long-range forces. And a slightly more detailed point again is you can actually mathematically work out how they decrease as they move away from each other, and they obey what is called the inverse square law. And what that means is that if I travel my gravitational field strength, if I travel away double the distance, so if I move twice as far away, so if we think about this distance here, where this mass is, as some distance r, some radius from the surface, if I was to double that distance, so I was to travel to a distance of 2r, and I was to have the same mass at this point, the gravitational field is double the distance, but it would be 4 times weaker at this point because it's further away. So it obeys the inverse square law, which means it gets weaker as you go away. That's the inverse. And the square, it doesn't just get like the same proportion. It will, however far away you've travelled, that number will be squared, that times weaker. So if I move 2 times further away, it gets 4 times weaker. 2 squared is 4. If I moved 3 times further away, that would be 3 squared. It would be 9 times weaker. If I moved 4 times further away, it would be 16 times weaker. 5 times 25, and so on and so forth. So it obeys that. That point is a slightly higher level point, but it is one that we should know nevertheless. So these are the basic properties of gravitational fields that you should know, first of all. So let's just relate this then to what would happen, how much force would something of 1 kilogram mass experience at a point in this field, okay? Now, when we think about gravitational fields in the lab, we have a slightly different picture that we have in mind. This is when we think of them on large scales. But in the lab, if we think of this as the ground, then if I was drawing the Earth's gravitational field in the lab, it would look slightly different. We would draw the gravitational field as looking like this. Because on short distances, like we have in the classroom, the gravitational field is constant everywhere inside the classroom. Here we can show that as we get further away from the Earth's gravitational field gets weaker. But in the classroom, gravitational field is the same everywhere. When you zoom in to, for example, if I was to zoom into this little part of the picture here, like really close at the surface, this is then what I would see. All the gravitational field lines are roughly the same distance apart. And so this shows the closer the field lines are, the stronger the field. So obviously here you can see the field lines spread out because it's radial as you move away. But at close distances, these lines, there are 3 words I could use to describe them. They are parallel, they are equidistant, and that just means they've got the same distance all the way across, and they're also perpendicular to the surface. And that's important because if I was to put a mass in this field, so I was to put a mass here, a mass m, it could just be a ball, for example, then it will experience a gravitational force that will act vertically downwards. And gravitational forces in the lab, we always imagine the force due to gravity, the weight acts vertically downwards. So in the lab, as far as we're concerned, the surface of the Earth's gravitational field is constant, and that constant is represented by G. Okay, so G on Earth is equal to 10 newtons per kilogram. And G is a number that you have to know. Okay, now G also has 2 names, so I want to just emphasize the 2 names. The first, when it's represented in units like I have here, is G is the gravitational field strength. And so what it does is it's a number that tells us what is the strength of Earth's gravitational field, and specifically at the surface. Okay, this only applies at the surface. If I was to think about Earth's gravitational field way out here in space, it would obviously be a lot weaker, so it would be less than 10. But on the surface of the Earth's gravitational field is 10. If I want to be really precise, it's actually 9.81, but for GCSE level, you're expected to know that it is 10, and that's what you have to remember. So you should be able to recall that. That is a spec point. Now, I also want to emphasize it has another name, and you have to know both names. The other name is acceleration due to gravity. So both of these terms you have to know because the exam board will use them interchangeably. And it is exactly the same thing. G is 10, but sometimes the units are given differently for acceleration due to gravity. It's given the units of acceleration, which are meters per second squared. So the key idea is you need to know that the Earth's gravitational field strength, the Earth's acceleration due to gravity is 10. Okay, and what that means is that if I have a 1 kilogram mass, so if this mass in this field is 1 kilogram, it will experience 10 newtons of force downwards at the surface of the Earth. What that means in terms of its acceleration is it will accelerate 10 meters per second every second. That's how much it will speed up by. So this idea of G being 10 on Earth is really, really important. So we use that in an equation that you will probably be familiar with, which is the equation for weight. Okay, so weight is the force due to gravity, and that, because it's a force, is measured in newtons. Okay, mass is different to weight, and that is measured in kilograms. So remember, weight is the force due to gravity. Mass is how much substance there actually is, and that's based on the density and the volume of an object. And then G is gravitational field strength, acceleration due to gravity, and as we've already said, G is equal to 10. So this is a number that you should know, and you won't be told necessarily in a calculation. You have to know it. And this gives you one really important exam technique thing that you need to know. Anytime you know the mass of an object, you know its weight. Anytime you know its weight, you know its mass, because this number G doesn't change on Earth. It's always 10. So if I've got the mass of an object, for example, if I've got a mass of 50 kilograms and I want to know the weight of that object, well, the weight is mass times G. So I'm going to do 50 times 10, and I have to know that 10. I have to know that I can do that, and that will give me the weight of the object as 500 newtons. So just notice the difference there between the weight and the mass. It's just multiplied by 10, and obviously there's the difference in units. So when we say I weigh myself and I then give an answer in kilograms, I'm not technically weighing myself, I'm really massing myself, I'm measuring my mass. If I was going to weigh myself, what I'd actually have to do is stand on a Newton meter, and I'd have to get an answer in newtons if I was being pedantic. So, as I say, really important exam tip. If you know the mass, you automatically know the weight. Now, there is one circumstance where you wouldn't automatically know it. Everything I've talked about here so far is if I'm on the Earth, okay? But obviously, if I compare the Earth, so G on the Earth is equal to 10 newtons per kilogram. That means 1 kilogram will experience 10 newtons of force on the surface of the Earth. But the moon or different astronomical bodies have different masses, and therefore different strengths of their gravitational field strength. I apologise, by the way, if I've cropped out part of the video earlier when I was writing it. So obviously you can now see what I've written retrospectively. I apologise for that. G on, say, for example, the moon. Now, the moon is about 6 times smaller than the Earth. So G on the moon is 1.6 newtons per kilogram. Jupiter, which is the largest planet in our solar system, has a much bigger mass, and therefore Jupiter has a G of 23 newtons per kilogram, or 22.9 if you want to be a bit more exact. But basically, other planets or other bodies could have different values of G. So if I was working out the weight of an object on a different body, like the moon or on Jupiter, then I'd have to use a different G. But on Earth, we use 10. If I'm on a different planet or a different body, then I will use whatever number that is. But I just want to stress, you have to know this number. You have to know that G on Earth is 10. You don't have to know it for anything else. If you're given an exam question where that's important, you will either be told it, or it might be that you have to work it out. So you might have to do weight divided by mass to work out G, which on Earth would be a really boring question because it would just be 10. but on any other planet, you then work out what the gravitational field strength is on that planet. So this is the broad overview of weight. I just want to relate this as a final point, and this is really just links to other parts of the course, to some other equations. So weight, which obviously is the main equation we've just talked about, is m times g. But this is actually based on a special case of Newton's second law. And Newton's second law is force is directly proportional to the rate of change of momentum. However, a special case of that is when we write it as F equals ma. So force is mass times acceleration. And I want you to realise that these two equations are the same because force, mass times acceleration, and weight is a type of force, but it's specific when the acceleration is because of gravity. So this equation is actually the same as F equals ma, it's just specific to gravity. That's the only difference. Another thing I want to relate to is how we can relate forces to energy. So if, for example, I have an object, like a ball, and I'm going to lift that object up to a certain height in a gravitational field. So I have a distance here that I've travelled, and I've got to use a certain amount of force to do that, okay? This process requires work being done. When we talk about the term work done in physics, what we mean, anytime you see the word work, I want you to relate that to energy. So work means energy. How much energy has been transferred? So I can write as a new equation, or an equation you may be familiar with. So energy is force times the distance travelled in the direction of that force. So in this equation, we have work done, which remember is another word for energy, or more specifically, energy transferred, because it's the amount of energy that I would transfer to lift this ball. How much work would I need to do that? And obviously, because this is a type of energy, that's measured in joules. Force is always measured in newtons, and distance is measured in meters. So if I know the force and I multiply that by the distance that I've travelled in that direction of that force, I then work out how much energy has been required to get to that point in the gravitational field. And the reason I just mentioned this equation is I can link these two things. I can link this equation for weight and this equation for work done to give me the equation for gravitational potential energy, which is weight times height, where height is the vertical distance and weight is always a vertical force because weight always acts vertically downwards. So gravitational potential energy, I can write as weight times height, or I can write it as mgh. So gravitational potential energy, which is the amount of energy required to lift an object in a gravitational field, is mass of the object that you're trying to lift multiplied by g, depending on what planet you're on. And obviously normally we're on Earth, so we know that g is equal to 10 newtons per kilogram, and then multiply that by the height that you're travelling. So this equation for weight is important because it relates to several others. And one final equation I'm going to mention, which is also important to this, is anytime you have an equation with energy, you have to be able to link that to power. Power is the rate at which energy is transferred. So power is measured in watts. And so here we would have energy or work done. And again, I just want to re-stress that work done is just another way that physicists like to describe the word energy. That's always measured in joules, divided by time in seconds. So power is how much energy you've transferred, but divided by how much time it's taken to transfer it. What's the rate at which you're transferring energy? So again, they could, as an exam question, could ask you to work out gravitational potential energy by first working out the weight, doing m times g, then times that by the height, and then divide that by the time to work out the power that you would need to lift a weight up to a certain height. All of these concepts are covered in other parts of P2 and also in P5, but I just want to relate this equation to weight that's important in this particular lesson to these other equations and make you realise how important this equation is because it links to so many others. You can also link the mass in this equation to, say, for example, density. So it's a really important equation for you to know in the course. It links to lots of different things. And even if you're not overly confident about these equations at the moment, please make sure you've noted it down. Please make sure you're aware of them. The equation for work done, force times distance travelled in the direction of that force, and power, energy divided by time, as important additional equations for you to know.